And then there'll be questions on functional equations in differentiability. Now we'll be given a function fx and we'll say this function fx is differentiable in the domain which is given in the question. So in such questions, what we'll do is we'll write f dash x as this limit h tends to 0 f x plus h minus fx upon h, and then using the functional equation given in the question, we're going to simplify this. And wherever we'll come across this condition, this limit h tends to 0 f a plus h minus f a upon h, we'll simply write this as f dash a. Say for example, in the question you'll find, suppose f0 is 0 and then you'll get f minus h upon minus h. So what we'll do is we can write this as this limit h tends to 0 f minus h minus f0 upon minus h, which is basically left hand derivative at 0, and since this function is differentiable, it will be equal to f dash 0. So we'll keep substituting particular values of derivative if they appear in the solution of this functional equation. Now here the question is, we are given this differentiable function such that f0 is 1 and it says f x plus y, it is equal to fx into f dash y plus f dash x into fy. Then we need to find the value of log f4 to the base e. Now if we find f dash x, we can write this as this limit h tends to 0 f x plus h minus fx upon h, and then it will be this limit h tends to 0. Now we can write this as fx f dash h plus f dash x fh minus fx whole divided by h. Now it says fx is a differentiable function and fx will be differentiable if it is 0 upon 0 indeterminate form, and it will be determinate form if fx into f dash 0 plus f dash x into f0 minus fx, it should be 0 for all x in the question. Now we already know the value of f0, we need to find the value of f dash 0, and for this what we'll do is, in this equation we'll put both x and y is 0, so it will be this f0. So this is f0 which is 1 and f0 is 1, it will be this f dash 0 plus this is f dash 0 and f0 is again 1. So value of f dash 0 is 1 by 2, and we put this value, we get fx by 2 plus f dash x minus fx equals 0, or f dash x equals fx by 2. Now we have to solve this differential equation. We write this as f dash x upon fx and it will be equal to 1 by 2. Now if we integrate, we'll write log fx and it will be equal to 1 by 2 x plus c. Now we take antilog, it will be this fx e to the power c into e to the power x by 2. Now when x is 0, y is 1. So it will be this 1 e to the power c into 1. So value of e to the power c is 1. So from here we can say value of fx is e to the power of x by 2. Now if we find f4, f4 is e square and log f4 it will be simply 2, and that is the answer to this question. Like the question is, we are given this function which is defined as fx plus y, that is equal to fx plus fy plus mod xy plus
xy square for all xy belongs to R, and it says f dash 0 is 0. Now if we put x and y as both 0, we'll get f0 as 0 as well. So at 0, fx is 0 and f dash x is 0. Now at 0, this function is continuous as f dash 0 exists. So we'll check its continuity at any general point. Now at x equal to a, its left hand limit will be f a negative, and there will be f a minus h. We can write this as f a plus f minus h plus mod a into minus h and a into h square. Now this is 0, and f minus h will be equal to f0, and that will be equal to 0. In the same way, f a plus h will again be equal to f a. So this function is continuous for all x belongs to R. Now we need to check its differentiability. Now we can write f dash x as this limit h tends to 0 f x plus h minus fx upon h. Now we can write this as this limit h tends to 0. Now fx plus h is fx plus fh plus mod x into h plus x into h square minus fx whole divided by h. Now this fx and fx will cancel, and f0 is 0. So we'll rearrange this as limit h tends to 0. We'll write this as fh minus f0 upon h plus, now here h and h will cancel, and here it is this xh. Now this is nothing but this is f dash 0. So we can write this as f dash x as f dash 0 plus mod x plus 0, and we are given that f dash 0 is 0. So basically f dash x is equal to mod x. Now since f dash x is continuous, this function is differentiable for all x belongs to R. So answer to this question is this option B, f is differentiable for all x belongs to R. Now here the question is, we are given two functions f and g, and it says f x plus y equals fx plus fy plus fx into fy, and fx is x into gx. And it says if limit x tends to 0, gx is 1, then which of the following statement is or are true? Now if we take this limit, this can be expressed as limit x tends to 0. Now this is fx upon x, and this is 1, and it will be 1 if it is indeterminate form. That means from here we can say value of f0, it must be equal to 0. Now if we find f dash x, it will be this limit h tends to 0, and this is f x plus h minus fx upon h, and this we can write as limit h tends to 0 fx plus fh plus fx fh minus fx whole divided by h. Now this fx will cancel. We can write this f dash x as, we'll take 1 plus fx common, and it will be this limit h tends to 0 fh upon h. Now we can write this as fh minus f0, because f0 is 0, and this is nothing but this is f dash 0. So we can write this as f dash x equals 1 plus fx into f dash 0, and this is some constant, say a. Now if we look at this limit, this is 0 upon 0 form. That means we can use L'Hopital's rule. We can write f dash 0 upon 1 will be equal to 1. So f0 is 0 and f dash 0 is 1. So if we put x as 0, f dash 0 is 1, f0 is 0, and that's your f dash 0. So value of f dash 0 is simply 1. So from here we can say f dash x is simply 1 plus fx. Now we can write this as f dash x upon 1 plus fx, that is equal to 1. Now we take its integral. We can write this as log 1 plus fx, and this is equal to x plus c. Now when x is 0, fx is 0, so it will be this log 1. So value of c is 0. So from here we can say log 1 plus fx equals x, or this fx is simply e to the power x minus 1. So our function fx is e to the power x minus 1. So for this function fx is e to the power x minus 1 and gx is e to the power x minus 1 upon x. Now f is differentiable at every x belongs to R, and if we find f dash x, it is e to the power x, f dash 1 is e, and f dash 0 is 1. So c is incorrect and d is correct. Now we look at this option B, and it says if g0 equals 1, then g is differentiable at every x. Now if we take this limit x tends to 0 gx, it is standard limit, so it is 1. So this gx is continuous at x equal to 0, and if it is continuous at 0, it is continuous in x belongs to R. Now this function will be differentiable everywhere, except we have to check its differentiability at x equals 0. So if we find g dash 0 negative, it will be this limit h tends to 0, and it will be e to the power minus h minus 1 upon minus h minus 1 upon minus h, and it will be this limit h tends to 0 e to the power minus h minus 1 plus h upon h square. Now this is limit h tends to 0. Now we'll use expansion of e to the power minus h. It will be 1 minus h plus h square upon 2 minus 1 plus h upon h square. Now this 1 will cancel, h will cancel. So this left hand derivative, it will be 1 by 2. Now we'll find g dash 0 positive. It will be this limit h tends to 0 e to the power h minus 1 upon h minus 1 divided by h. Now this is limit h tends to 0 e to the power h minus 1 minus h upon h square. Now again we'll use expansion. So it will be this limit h tends to 0 1 plus h square upon 2 and higher powers minus 1 minus h upon h square. Now it will cancel. This is 1 by 2. So this function gx, it is differentiable at x equal to 0, and therefore it is differentiable in x belongs to R. So the correct options are A, B and D. Right, the question is gx is a polynomial satisfying gx into gy, it is equal to gx plus gy plus gxy minus 2. Now what we'll do is we'll find the value of g1. Now we'll put x and y as both 1. We can write g1 square will be equal to 2 times g1 plus g1 minus 2. So it will be this g1 square minus 3g1 plus 2 equals 0. That means value of g1 is either 1 or value of g1 is 2. Now if we put y as 1 in this, taking g1 as 1, we'll get gx and will be equal to gx plus 1 plus gx minus 2. From here we'll get this condition that gx is a constant function, but it says g2 is equal to 5. That means g1 is not equal to 1. So g1 has to be 2. Now what we'll do is we'll replace y with 1 by x. Now if we replace y with 1 by x, we can write gx into g1 by x, it is equal to gx plus g1 by x plus g1 minus 2. Now g1 is equal to 2, so it will cancel. So from here we get this condition that gx plus g1 by x minus gx g1 by x, it is equal to 0. Now we'll subtract 1 both sides. Now we'll take this together and this together. So we can write gx minus 1, and here we'll take minus g1 by x common, and then it will be gx minus 1. This is equal to minus 1. We'll factorize and multiply this minus 1 here. We can write gx minus 1 into g1 by x minus 1, it is equal to 1. Now it is given that gx is a polynomial and gx minus 1, they should cancel x for all the values of x. So that means this gx minus 1, it should be of the form plus or minus x to the power n. So from here we get gn as plus or minus x to the power n plus 1. Now here we must decide if it is plus sign or minus sign, because it cannot be both. Then in that case this gx, it won't be a function. Now it is given that g2 is 5. Now we write x as 2, so it will be plus minus 2 to the power n plus 1. So from here we can say it is a plus sign and value of n is 2. So this function gx, it will be simply x square plus 1. Now here we need to find the value of this limit x tends to 3 gx. Limit x tends to 3 and gx is x square plus 1. So this is 9 plus 1, 10. And that's your option C. Now the question is, a function is defined as fx upon y, it is equal to fx minus fy, and if f is differentiable on 0 to infinite and this limit x tends to 0, f1 plus x upon x, it is equal to 3, then determine the value of fx. Now if we put x and y as both 1, we'll get f1 equals f1 minus f1. That means value of f1 must be 0. Now we can write this as this limit x tends to 0, f1 plus x minus f1 upon x, and it is equal to 3. Now this is nothing but this is f dash 1. So now we also have value of f dash 1, and which is 3. Now if we write f dash x, it will be this limit h tends to 0, and this is f x plus h minus fx upon h. Now fx minus fy is fx upon y. So we can write this as this limit h tends to 0, and this is f1 plus h upon x divided by h. Now we'll multiply and divide it with x. Now this is nothing but this is f dash 1. So it will be this f dash 1 by x. Now f dash 1 is 3, so this is 3 by x. Now once we have this f dash x as 3 by x, all we need to do is we need to integrate. We can write fx as 3 log x plus c. Now f1 is 0, so if we put x as 1, y is 0. So this is 0, this is 0 plus c, that means value of c is 0. So our function fx in this case will be simply 3 log x. So this fx is simply 3 log x, and that is the answer to this question. Now the question is, a differentiable function satisfies this relation, which is fx plus y, that is equal to fx plus fy plus 2xy minus 1 for all xy belongs to R, and says if f dash 0 is under root of 3 plus a minus a square, find fx and prove that fx is greater than 0 for all x belongs to R. Now we'll find the value of f0, and for that we'll put x and y as both 0. So this is f0, and here will be 2 times f0 minus 1. So from here we can say value of f0, it must be 1. Now we can write f dash x as limit h tends to 0. Now it will be this fx plus h minus fx upon h. Now fx plus h is fx plus fh plus 2xy minus 1. So it will be this limit h tends to 0, and then it will be this fx plus fh plus 2xh minus 1 and minus fx whole divided by h. Now this fx and fx will cancel. Now we can rewrite this as limit h tends to 0, and here it will be fh minus 1, and we can write this one as f0 upon h and plus 2x. Now this is nothing but this is f dash 0. So we can write this f dash x as f dash 0 plus 2x. Now we integrate this, we can write fx equals, now this 2x is simply x square, and here will be this f dash 0x and plus c. Now when x is 0, f0 is 1. So this is 1 and it is equal to c. So value of c is 1. So we can write this function fx as x square plus, and then f dash 0 is defined as 3 plus a minus a square x and plus 1. Now we need to show that this function is positive for all x belongs to R. Now basically it's a quadratic equation. Now if we write its discriminant will be b square, which is 3 plus a minus a square and then minus 4ab. So there will be minus 4. Now we can write this as minus a square plus a minus 4, and this is always negative. And when d is less than 0 and coefficient of x square is positive, that means this fx is greater than 0 for all x belongs to R. And this is what we need to prove in this question. Now here we have 4 questions. 1, 2, 3 and 4. Now we'll start with this first one, and it says let fx be defined on minus a to plus a with a greater than 0, and assume that f is continuous at x equals to 0. That means f 0 minus h is equal to f 0 plus h, and it will be equal to f0. It is given that limit x tends to 0, fx minus f kx upon x, it is equal to alpha, where k lies between 0 and 1. Then compute f dash 0 positive and f dash 0 negative, and comment on differentiability of f at x equals 0. Now what we'll do is we'll first solve this limit. Now if we take its left hand limit, it will be this limit h tends to 0, and this is f minus h minus f k into minus h upon minus h, and this value will be alpha. Now what we'll do is we'll subtract f0 and we'll add f0. Now we can write this as this limit h tends to 0. Now this is f minus h minus f0 upon minus h, and then if we take this minus common, it will be this limit h tends to 0 f minus kh minus f0 upon minus h, and this is equal to alpha. Now this is nothing but this is left hand derivative at 0, so it will be this f dash 0 negative, and here if we multiply and divide it with k, now this again is 0 minus kh minus f0 upon minus kh, so it will be left hand derivative at 0. So this is k into f dash 0 negative, that is equal to alpha. So from here we can say value of f dash 0 negative is alpha upon 1 minus k. Then the same way, we'll find its right hand limit. Now for this right hand limit, we can write limit h tends to 0 fh minus fkh upon h. Now we'll subtract f0 and add f0, and this is equal to alpha. So it will be this limit h tends to 0 fh minus f0 upon h minus this limit h tends to 0 fkh minus f0 upon h, that is equal to alpha. Now here again we'll multiply and divide it with k. Now these are right hand derivative at 0. So it will be f dash 0 positive minus k into f dash 0 positive, that is equal to alpha. So value of f dash 0 positive will be alpha upon 1 minus k. And since they are equal, f dash 0 exists and the value of f dash 0 will be alpha upon 1 minus k. And therefore this function is differentiable at x equals 0. Now the second question is, we are given this function f from R to R defined by this equation fx plus y equals fx into fy, and it says function is differentiable at x equals to 0 and f dash 0 is 2. Now show that f dash x equals 2fx for all x belongs to R, and hence determine fx. Now what we'll do is we'll find the value of f0, and for that we'll put both x and y as 0. Then we can write this as f0 equals f0 square. So from here we get two conditions, that either f0 is 0 or f0 is 1. But in this equation, if we put y as 0, we get fx equals fx into f0, and if f0 is 0, then this function fx will be a constant function, and then this f dash 0, it cannot be 2. So we'll discard this possibility that f0 is 0. So from here we can say value of f0 is 1. Now we'll find f dash x. Now f dash x is defined as this limit h tends to 0 f x plus h minus fx upon h. Now we know fx plus h will be fx into fh. So we can write this as this limit h tends to 0 fx into fh minus fx upon h. Now we'll take this fx common and we'll take it, or this limit. So it will be this limit h tends to 0 fh minus 1 upon h. Now we can also write this as fx and then this limit h tends to 0. Now this is fh minus, and we can write this one as f0. So it will be fh minus f0 upon h, which is nothing but f dash 0. So we can write this f dash x as fx into f dash 0, and f dash 0 is 2. So from here we can say this f dash x will be 2 times fx, and this is what we need to prove. Now we need to find fx also. So what we'll do is we'll use differential equation. You can write this as f dash x upon fx will be equal to 2, and we integrate, we can write log fx and it will be equal to 2x plus c, or fx will be e to the power 2x into e to the power c, and e to the power c is some constant. Now we know that when x is 0, fx is 1. So if we put x as 0 and fx is 1, then value of e to the power c is 1. So from here we can say our function fx is e to the power 2x. And that is what we need to find in this question. Now this third question is, let fx be a real valued function not identically 0, satisfying the equation f x plus y to the power n, it is equal to fx plus f y to the power n, where n is an odd natural number and it is true for all real xy, and f dash 0 is greater than or equal to 0. Now we need to find the value of f10. Now first we'll find the value of f0. Now if we put x and y both 0, it will be this f0, this is f0, and this is f0 to the power n. So from here we can say value of f0 is 0. Now we write f dash x. Now f dash x will be this limit h tends to 0, f x plus h minus fx upon h. Now we write this h as this limit h tends to 0, f x plus h to the power 1 by n to the power n minus fx upon h. Now we know that fx plus y to the power n is fx plus fy to the power n. So we can write this as this limit h tends to 0, and will be this fx plus fy, which is fh to the power 1 by n whole to the power n minus fx divided by h. Now this fx and fx will cancel. Now if we put x as 0, we can write f y to the power n is fy whole to the power n. That means we can take this power out of this function, or we can put this power inside this function. So if we put this power inside this function, we can write this as this limit h tends to 0, f h upon h. Now f0 is 0, so we'll write this as fh minus f0 upon 0, and this is nothing but this is f dash 0. Now let f dash 0 is some constant, say a. So now we have f dash x equals a. Now we integrate, we can write fx equals ax plus c. Now when x is 0, f is 0, so clearly value of c is 0. Now we need to find one more value to find the value of a. So we'll again go back to the equation. So if we put x as 0 and y as 1, we can write f1 and it will be equal to f0, which is 0, plus f1 to the power n. So from here we'll get either f1 is 0 or f1 is 1. Then in that case, this fx will be 0 throughout constant, but it is given that it is not identically 0. That means value of f1 is to be taken as 1. So if we put x is 1, fx is 1. So value of a is 1. So in this case, fx is simply x. We need to find the value of f10. Value of f10 is 10. Now this fourth question is, we are given this function f, and it says if this function is differentiable at 0, then show that it is differentiable for all x belongs to R. Now if it is differentiable at 0, that means f dash 0 negative must be equal to f dash 0 positive. And we'll take this as sum f dash 0. Now we need to show that this function is differentiable for all x. Now what we'll do is we'll find f dash x. Now f dash x will be this limit x tends to 0, and this is f x plus h minus fx upon h. Now in this equation, what we'll do is we'll take x as 3x and y as 3h. Then we can write f x plus h will be f3x plus f3h plus f0 upon 3. And the same way we put x as 3x and y as 0, we can write fx as f3x plus 2f0 upon 3. So now we can write this f dash x as this limit x tends to 0 f3x plus f3h plus f0 minus f3x minus 2f0 whole divided by 3h. Now f3x will cancel, so we can write this as this limit x tends to 0, and this is f3h minus f0 upon 3h, which is nothing but f dash 0, which is some constant, say a. Now this fx, it is ax plus b. So this function, if it is differentiable at 0, it is differentiable for all x belongs to R. Now here the question is, we are given that fxy, it is equal to xfy plus yfx for xy belongs to R positive, and says it is differentiable on 0 to infinite. Now what we'll do is we'll find the value of f1. Now we'll put x and y as both 1, so it'll be this f1 and it'll be equal to f1 plus f1. So clearly value of f1 is 0. Now we'll find f dash x. Now this f dash x will be this limit h tends to 0 fx plus h minus fx upon h, which is this limit h tends to 0, and this is f, and x into 1 plus h upon x minus fx upon h. Now this is fx into y. Now we can write fx into y as xfy plus yfx. So it will be this limit h tends to 0, will be this x f 1 plus h upon x and plus 1 plus h upon x into fx minus fx whole divided by h. Now we'll split it in two parts. Now we can write this f dash x as, now we'll take x common from this, and it will be this limit h tends to 0 f 1 plus h upon x divided by h, and we can write this as f1 because f1 is 0. And here if we cancel this fx, h and h will cancel, it will be simply f x by x. Now if we multiply and divide by x, now this x will cancel, this is f dash 1. So we can write this f dash x as f dash 1 plus f x upon x. Now we can write this as dy by dx, and we'll take it on the left hand side. So this is minus y by x, and this is f dash 1, which is linear differential equation in y. Now first we'll calculate its integrating factor. Its integrating factor will be e to the power minus integral of 1 by x dx, which is e to the power minus log x, which is simply 1 by x. So we'll get this as y, which is fx into 1 by x, and then into this integral f dash 1 by x into dx. Now this is fx upon x, and it is f dash 1 ln x plus c, or we can write fx equals f dash 1 into x log x plus cx. Now we know that f1 is 0. So if we put x as 1, we'll get c as 0. So our function fx will be simply f dash 1 into x log x, and that is the answer to this question. Now here we are given that e to the power minus xy into fxy, it is e to the power minus x fx plus e to the power minus y fy for all xy belongs to R positive, and f dash 1 it is equal to e. Now we'll find the value of f1 also. Now if we put x and y as 1, we can write e to the power minus 1 f1 equals e to the power minus 1 f1 plus e to the power minus 1 f1. Now from here we can say value of f1 is 0. So we have f1 and we also have f dash 1. Now what I'll also do is I'll write this fxy as e to the power xy into e to the power minus x fx plus e to the power minus y fy. Now we'll find f dash x. Now we'll write this f dash x as this limit h tends to 0 fx plus h minus fx upon h, and we are going to write this as limit h tends to 0, and we'll take this x common. It will be x into 1 plus h upon x minus fx by h. Now this is limit h tends to 0. Now this is fxy, and fxy is e to the power xy, which is e to the power x plus h, and then e to the power minus x fx plus e to the power minus 1 plus h upon x into f1 plus h upon x minus fx whole divided by h, and that's your f dash x. Now if we multiply it, then we'll write f dash x as this limit h tends to 0. Now it will be this e to the power h fx plus, and here it will be e to the power x plus h minus 1 minus h upon x, and this is f1 plus h upon x minus fx whole divided by h. Now we'll take fx together. We can rearrange this as this limit h tends to 0 fx into e to the power h minus 1 upon h, and then plus this limit h tends to 0, and here it is e to the power x plus h minus 1 minus h upon x f1 plus h upon x. Now we know that f1 is 0, so we can write this as f1 whole divided by h. Now we'll multiply and divide it with x also. Now this is f dash x, and this is standard limit 1, so it will be this fx plus, now if we put h as 0, this is e to the power x minus 1 upon x into, and this is derivative of f at 1, and there will be f dash 1. Now we are given that f dash 1 is e. So if we put f dash 1 as e, we can write this as f dash x equals fx plus e to the power x upon x. Now if we multiply it with e to the power minus x, we can write e to the power minus x f dash x minus e to the power minus x fx, it is equal to 1 upon x, and this is nothing but this is derivative of e to the power minus x into fx. So it will be d by dx of e to the power minus x into fx, it is equal to 1 by x. Now we integrate this, we can write e to the power minus x fx, and it will be equal to log x plus c. Now when x is 1, fx is 0. So clearly value of c is 0. So we can write our function fx as e to the power x into log x. And that is the answer to this question. Now question number 26 is, we are given this function f x minus y equals fx upon fy. Now this condition, it is satisfied by exponential function. So here this fx, it must be a to the power x. Now if we find f dash x will be a to the power x log a. Now f dash 0 will be a to the power 0, which is 1, and then log a, and f dash 0 is p. So from here we can say value of log a is p. Now if we find f dash 5 will be a to the power 5 log a, and it is q. Now log a is p. So from here we can write a to the power 5 equals q by p. Now we need to find the value of f dash minus 5. Now f dash minus 5, it will be a to the power minus 5 into log a. Now 1 upon a to the power 5 will be p by q, and log a is simply p. So this value will be p square by q, and that's your option D. Now here the question is, let fx plus y is equal to fx plus fy for all xy. And it says, if fx is continuous at x equals 0, then show that fx is continuous at all x. And that's our first question. Now, if we put x and y both 0, then we'll get f0 equals f0 plus f0. That means a value of f0 must be 0. So for this function, f0 is 0. Now it says fx is continuous at 0. And if fx is continuous at 0, that means f0 minus h must be equal to f0 plus h, and it will be equal to f0, and f0 in this case is 0. Now we need to show that it is continuous for all x. Now if we take any x belongs to R, then left hand limit at any x will be f x minus h. Now it is given that fx plus y is fx plus fy. So we can write this as fx plus f minus h. Now f minus h is f0, which is 0. So it will be equal to fx. And if we look at its right hand limit, which is fx plus h. Now fx plus h is fx plus fh. Again this fh is 0. So this is also equal to fx. So for any real x, fx minus h will be equal to fx plus h, and it is equal to fx. That means this function is continuous for all x belongs to R. Now the question is, a function is defined on -1 to 1 to minus pi by 2 to plus pi by 2. It satisfies this equation, which is fx plus fy. It is fx into under root of 1 minus y square plus y into under root of 1 minus x square. Now first is show that fx is an odd function. So what I'll do is I'll replace y with minus x. So now I'll be this fx plus f minus x, and here it will be fx into under root of 1 minus x square, and then minus x into under root of 1 minus x square, which is nothing but f0. Now we need to find the value of f0, and for that what we'll do is we'll put both x and y as 0. So then it will be 2 times f0, and here it will be this f0. So clearly value of f0 is 0, which is 0. So from here we can clearly say f of minus x is minus fx. Therefore this function is an odd function. Now second is, if f is differentiable on -1 to 1 and f dash 0 is 1, then show that f dash x is 1 upon under root 1 minus x square. Now what we'll do is, for the second part, we are given that f dash 0 is 1 and this function fx is differentiable. So we can write f dash x as this limit h tends to 0, and it will be f x plus h minus fx upon h. Now we have already proved that this f is an odd function. We can write minus fx as f minus x. So it will be this limit h tends to 0, and we can write this as fx plus h plus f minus x upon h. Now this is fx plus fy. So now we'll write this as this limit h tends to 0, and here it will be this f x plus h under root 1 minus x square, and then minus x into under root of 1 minus x plus h whole square whole divided by h. Now what we'll do is we'll let x plus h under root of 1 minus x square minus x under root of 1 minus x plus h whole square as t. Now as h tends to 0, it will be x into under root 1 minus x square, and here it will be minus x into under root 1 minus x square. So as h tends to 0, t tends to 0. Now we can write this as this limit t tends to 0, and this is ft. Now we'll multiply and divide with t also. So it will be this t and then t upon h. Now ft upon t is basically f dash 0. So we can write this as f dash 0 into this limit t tends to 0 and then t by h. And the question says f dash 0 is 1. So we'll put this as 1, and we'll again put back this value of t. So we'll write this f dash x as limit h tends to 0, and here we'll take x together and h together. So it will be this x into under root of 1 minus x square minus under root of 1 minus x plus h whole square and plus h into under root of 1 minus x square whole divided by h. Now in this part h and h will cancel. So we let this f dash x as under root of 1 minus x square and then plus this limit h tends to 0, and this is x, and here we'll rationalize it, and if we rationalize it we get 1 minus x square and then minus 1 plus x plus h whole square upon h, and then into under root of 1 minus x square plus under root of 1 minus x plus h whole square. Now this is f dash x, this is under root of 1 minus x square, and this is limit h tends to 0, and this is x. Now here 1 and 1 will cancel, x square will also cancel, so we'll get this as 2hx plus h square upon h into under root of 1 minus x square plus under root of 1 minus x plus h whole square. Now we'll cancel this h and we'll put this limit h tends to 0. So we'll get this f dash x as under root of 1 minus x square plus 2x square upon 2 times under root of 1 minus x square. Now this 2 and 2 will cancel. Now we take this LCM, it will be under root of 1 minus x square and 1. So we have proved that f dash x is 1 upon under root of 1 minus x square. And that's our second part. F dash x is 1 upon under root of 1 minus x square. Now from this we have to determine the value of fx. Now f dash x is 1 upon under root of 1 minus x square. Now we integrate this. Now this is fx, and here this is sin inverse x plus c. Now when x is 0, f0 is 0. That means c is 0. So basically this function fx is sine inverse of x. And that is the answer to this question. Now the question is, a twice differentiable function f, it satisfies this relation, which is f x square plus y square, and it is equal to f x square minus y square plus f 2xy. It is given that f0 is 0 and f double dash 0 is to find the value of fx. Now if we put x as 0, then we can write f y square, it is equal to f minus y square plus f0, and f0 is 0. So from here we can say fh, it is equal to f minus h. And since this function is differentiable, it will be equal to f0, which is 0. Now we'll find f dash x. Now what we'll do is, we'll take this equation, which is f x square plus y square, and it is equal to f x square minus y square plus f 2xy, and we'll subtract fx square and we'll divide everything with y square. Now we'll take this limit y tends to 0. Now this is limit y tends to 0, and this is also limit y tends to 0, and this is limit y tends to 0. Now this is derivative of this function at x square. So this is f dash x square. Now here, since this is minus y square, we'll take minus here, when we'll put minus here, so this is minus, and this also is derivative of x square. This is right hand derivative and this is left hand derivative, and plus this limit y tends to 0 f 2xy upon y square. Now if we put y as 0, f0 is 0 and y is 0, so this is 0 upon 0 form. So we can write 2f dash x square, it will be equal to this limit y tends to 0. Now this is f dash 2xy into 2x upon 2y. When we differentiate this with respect to y, we can say f dash y square into 2y, it is equal to f dash minus y square minus 2y. Now for y equal to 0, we'll always get f dash y square is equal to minus f dash minus y square. If we put y as 0, we'll get f dash 0 as 0. Now again, this is 0 upon 0 form. Now we multiply it with x and divide it with x. This is second derivative of this function at 0. So it will be f double dash 0. So we can write 2 times f dash x square, it will be f double dash 0 into 2xy. Now this 2 and 2 will cancel, and f double dash 0, it is given as 2. So we can write f dash x square, it is equal to 2x square, or simply f dash x equals 2x. Now if we integrate this, we get fx as x square plus c. Now we know that when x is 0, f is 0, that means c is 0. So our function fx in this case is simply x square. And that is the answer to this question. Now we'll solve this second question, which is if fx into y is fx into fy for all xy and fx is continuous at 1, then prove that fx is continuous for all x except x equals to 0. And we are given that f1 is unequal to 0. Now it says fx is continuous at x equals 1. Now that means f1 minus h will be equal to f1 plus h, and they'll be equal to f1, and none of it is equal to 0. Now if we look at any point A which is R except 0, then we can write left hand limit as limit h tends to 0, f a minus h. Now it will be this limit h tends to 0. Now we can write this as f, and if we take a common, it will be a into 1 minus h upon a. Now fx into y is fx into fy. So we'll write this as limit h tends to 0, fa into f 1 minus h upon a. Now f1 minus h upon a is f1 negative, which is f1 minus h, and it will be equal to f1. So this is fa into f1. And the same way, we want to write its right hand limit. Now, right hand limit will be limit h tends to 0, and then a be this f a plus h, which is this limit h tends to 0, f a into 1 plus h upon a, which again is fx into fy. So it is limit h tends to 0, f a into f 1 plus h by a. Now this is f1 plus h, which is right hand limit at 1, which again is f1. So this is fa into f1. Now if we look at this function again, we're given that fxy equals fx into fy. Now if we put both x as 1 and y as 1, we can write f1 equals f1 square, which is a quadratic in f1. So from here we'll get this condition that either f1 is 0 or f1 is 1. Now f1 is unequal to 0, it is given in the question. So the only condition that we have here is value of f1 is 1. Now if we put f1 is 1, then this is fa and this is also fa. So for all the points a which are r minus 0, fa negative is equal to fa positive, and will be equal to fa. That means this function is continuous for all such a's. Now what will happen at a equals 0? Now at a equals 0, if we look at its left hand limit, its left hand limit will be limit h tends to 0, f minus h, which is f minus 1 into f0, and this f minus 1 may not be equal to 1. So at a equals 0, it may be continuous and it may be discontinuous. So it is not necessarily true. So this function is continuous for all x except at 0. And one counter example can be if we take this function fx as 1 upon x when x is equal to 0 and 0 at x equal to 0. Now this function, it satisfies all the conditions and it is continuous for all x belongs to r minus 0, and at 0 this function is discontinuous. Now here the question is, we are given that a function f is such that fx plus y cube is equal to fx into f y cube, and if f is continuous at x equal to 0, prove that f is continuous everywhere. That means if f minus h is equal to fh is equal to f0, then this function is continuous everywhere. What we'll do is, first we'll find the value of f0. Now we'll put x and y as both 0. We can write f0 equals f0 to the power 4. So the value of f0 is either 0 or the value of f0 is 1. If we take f0 as 0, then this, if we put x as 0, then we get fy cube equals 0. So this function will be a constant function everywhere, for which this function f is continuous. So we'll take the second case when the value of f0 is 1. Now if we take f0 as 1, then if we check its continuity at any point, say x equal to a, which is the real number, then we can write f a plus h as f a plus h cubed to the power 1 by 3. Now this is f a into f h cube to the power 1 by 3. Now if we put x as 0, we can write fy cube. Now f0 is 1 and this is fy whole cube. So we can write this as fa into fh whole cube to the power 1 by 3. I'll cancel. Now this fh, it is equal to f0 and f0 is 1. So this is equal to fa. In the same way, if we write f a minus h, it will be f a minus h cube to the power 1 by 3. So it is fa and then f minus h cube to the power 1 by 3. Using same logic, we can write fa and this is f minus h 3 to the power 1 by 3 and f minus h is f0 and f0 we have taken as 1. So this is also equal to fa. So in this case, fa negative is equal to fa positive and they are equal to fa. So this function is continuous everywhere. Now here the questions, we are given that fx minus fy is less than or equal to x minus y cube. Now we can write this as mod of fx minus fy upon x minus y. It is less than or equal to mod of x minus y square. We'll take this limit y tends to x both sides. This is limit y tends to x. Now this is mod of f dash x and it is less than or equal to 0. Now mod function cannot be negative. So from here we get f dash x equals 0. That means this fx is a constant function. This is what we need to prove in this question. Now the question is, if fx plus y is equal to fx into fy for all x and fx is 1 plus gx into capital Gx, where this limit x tends to 0, gx is equal to 0 and this limit x tends to 0, gx, it exists, then prove that f is continuous at all x belongs to R. Now if we put x and y is both 0, we can write f0 is equal to f0 square. So from here either f0 is 0 or f0 is 1. Now if we put y as 0, fx into f0 is 0, which is a constant function. So for this, fx will be a constant function which is continuous for all x belongs to R. Now what if f0 is 1? So we'll take this case when the value of f0 is 1. Now we'll check for continuity of fx at x equals 0. Now f0 negative, it will be 1 plus g0 negative into g0 negative. Now g0, it is 0. That means this f0 negative is 1. And f0 positive is 1 plus g0 positive and g0 positive. Now this again is 1. So that means this function fx is continuous at x equals 0. Now if fx is 0, then this limit, it cannot be 0. So we have to discard this possibility f0 equals 0. So the only condition that remains here is value of f0 must be 1. Now once we know that f is continuous at 0, that is fh equals f minus h and it is equal to f0, which is 1. We have to prove that it is continuous for all x belongs to R. Now we'll check for its continuity at any point x equals a. Now f a positive is f a plus h. Now it will be this f a into fh and fh is simply 1. So it will be equal to f a, and the same way f a negative is f a minus h, which is f a into f minus h, and f minus h is again 1. So it is equal to f a. So for any point a, f a positive is equal to f a negative is equal to f a. That means this function f is continuous at all the points. Here the question is, we are given this function fx, which is a differentiable function satisfying this relationship, which is f square x plus f square y plus 2 xy minus 1, it is equal to f square x plus y. For all x belongs to R, it is given that fx is always greater than 0 and value of f root 2, it is equal to 2. We need to determine this function fx. Now if we put both x and y as 0, we'll get 2 times f square 0, and this is minus 2, and it will be this f square 0. So from here we'll get the value of f0 as root 2. So value of f0 is root 2. And this equation, what we'll do is we'll replace y with h. So we can write f square x plus h will be equal to f square x plus f square h plus 2 xh minus 1. Now we'll take this x on the left hand side. We can write f square x plus h minus f square x, and will be equal to f square h plus 2 xh minus 2. Now we'll divide everything with h. Now this is limit h tends to 0, both sides. Now we'll split this as limit h tends to 0 f x plus h minus fx upon h into fx plus h plus fx, and here we'll write this as this limit h tends to 0. We'll take these two together, so it will be this f square h minus f square 0 upon h and plus this 2x. Now this is f dash x and this is simply 2fx, so it is 2fx into f dash x, and here it is fh minus f0 and fh plus f0. Now fh plus f0 is 2 times f0, and then fh minus f0 upon h is f dash 0 and plus 2x. Now this is some constant. We'll cancel this 2 with 2. So we can write fx into f dash x as x plus a. Now if we integrate this, we can write fx whole square upon 2. It will be x square upon 2 plus ax plus c. So basically this function fx, it will be under root of x square plus 2ax plus some constant c dash. Now we are given two conditions. One of them is f0 is root 2 and f2 is 2. Now if we put x as 0, we'll get this as root 2 and will be equal to c dash. So value of c dash is 2. And if we put x as root 2, we can write 2 equals under root of 2 plus 2ax plus 2. Now we square it, we get a equals 0. So a is 0 and c dash is 2. So basically our function fx will be under root of x square plus 2, and that is the answer to this question. Now the question is, we are given a function which is defined as fxy equals 2fx minus fx upon y. It is differentiable on R positive such that f1 is 0 and f dash 1 is 1. Now this first part is show that fy is equal to minus f1 upon y. So what we'll do is we'll simply put x as 1. So it will be this fy equals 2f1 minus f1 upon y. Now f1 is 0. So from here we can say fy is equal to minus f1 upon y. That means this first we have proved. Now second is prove that fx plus fy equals fx upon y. Now we are given that fxy equals 2fx minus f x upon y. Now if we interchange x, y, we can write f y x as 2fy minus f y by x. Now if we equate these two, then we can write 2fx minus f x upon y, it is equal to 2fy minus f y by x. Now minus f 1 upon y is fy. So we can write this as this is plus f x upon y. Now if we rearrange this, we can write 2fx minus fy, it will be equal to 2f x upon y. This 2 and 2 will cancel. So here it should be this minus and not plus. So that's our second result. Now third one is hence determine fx. Now what we'll do is we'll write f dash x. Now f dash x is this limit h tends to 0 f x plus h minus fx upon h. So it will be this limit h tends to 0. Now fx minus fy is fx upon y. So it will be this f1 plus h upon x, and this is h. Now we'll multiply and divide it with x. Now we are given that f1 is 0. So we'll write minus f1. Now this is nothing but this is derivative of this function at 1. So it will be this f dash 1 upon x. Now f dash 1 is also 1. So this is 1 by x. So our function is defined such that f dash x is 1 by x. Now we integrate this, we can write fx equals log x plus c, and f1 is 0. So log 1 is 0 plus c. So from here we get c is 0. So in this case, this function fx is simply log x, and that is the answer to this question. Now the question is, a differentiable function f, it satisfies the relation fx plus y plus f xy minus 1, and it is equal to fx plus fy plus fx into y for all xy belongs to R, and it says f1 is 2, f dash 0 is 1, and f dash minus 1 is minus 1. Find fx. Now again for this, what we'll do is we'll write f dash x. So this f dash x will be limit h tends to 0 fx plus h minus fx upon h. Now we'll replace y with h, and we'll use fx plus h minus fx from this equation. So it will be this limit h tends to 0, and here it will be this fh plus fxh minus fxh minus 1 whole divided by h. Now here we need the value of f0. So what we'll do is we'll put x and y as both 0. Now if we put x and y as both 0, we can write f0 plus f minus 1 will be equal to 3 times f0, or f minus 1 is 2 times f0. Now what we'll do is we'll add f minus 1 and we'll subtract 2 f0. Now we can rearrange this as this limit h tends to 0. One of the f0 we'll take it with fh. So it will be this fh minus f0 upon h plus this limit h tends to 0. One of them we'll take it with xh. So it will be hx minus f0 upon h. And then finally we have this minus, and then this limit h tends to 0 f minus 1 plus xh minus f minus 1 upon h. Now this is f dash 0. Now here we'll multiply and divide everything with x. This again is f dash 0, so it will be this f dash 0 x, and minus here also we'll multiply and divide everything with x. Now this is derivative of this function at minus 1, so this is x into f dash minus 1. Now f dash 0 is 1 and f dash minus 1 is minus 1, so it will be this 1 plus x and plus x, so it will be simply 1 plus 2x. So in this case f dash x is 1 plus 2x. Now if we integrate, we can write fx as x plus x square plus c. Now we are given that f1 is 2. So this is 2 and this is 1 plus 1 plus c implies c equals to 0. That means our function fx is x plus x square, and that is the answer to this question.
Now question number 2 is, let R denote the set of real numbers. Find all the functions f R to R satisfying mod of fx minus fy, and it is equal to 2 x minus y. Now taking x as x plus h and y as x, we can prove that this function is a continuous and differentiable function. Now if we write this function as fx minus fy upon x minus y mod equals 2, and if we take this limit y tends to x, then we get mod of f dash x, it is equal to 2, or we can write f dash x equals plus or minus 2. Now we'll integrate this function. We can write this as fx equals plus minus 2x plus c. So there will be two such functions. One of them will be 2x plus c and the other one will be minus 2x plus c.
Now here the question is, fx is defined for x greater than minus 1, and it says if f0 is 1 and f dash 0 is 0 and 1 plus fx into f double dash x, it is equal to 1 plus x, and if x is greater than 0, then f dash x is which of the following? Now if we look at f double dash x will be 1 plus x upon 1 plus fx. Now since this function has a continuous derivative and f double dash x exists, that means this 1 plus fx, it must not be equal to 0. So it will be either always positive or it will be always negative. That is given that at 0 this value is 1, so at 0 this value is positive, so that means this 1 plus fx, it will be greater than 0 for all x greater than 0, and this 1 plus x is also positive. That means f double dash x is greater than 0 whenever x is greater than 0. Now it implies that f dash x is an increasing function, and if x is greater than 0, then f dash x, it will be greater than f dash 0, as this function is increasing, and the value of f dash 0 is 0. So from here we can say value of f dash x is always greater than 0. That means f dash x is always positive, and that's your option A. Now here the question is, we are given that f x plus y by 3, it is equal to fx plus fy plus 2 whole divided by 3 for all xy belongs to R, and it is given that f dash 0, it is equal to 2, then which of the following statements is or are true? Now first we will find the value of f0, and for that we will put x as 0 and y as 0. Now this will be f0, and it is 2f0 plus 2 divided by 3. That means value of f0 is simply 2. Now we replace this 2 with f0. The condition becomes f x plus y by 3 will be equal to fx plus fy plus f0 upon 3. Now we have already proved this question, but we are going to do it again. Now we'll write f dash x is this limit h tends to 0 f x plus h minus fx upon h. Now we can write fx plus h as this limit h tends to 0 f 3x plus 3h by 3 minus f 3x plus 0 by 3 whole divided by h. Now we'll use this formula. So if we use this formula, we can write this as limit h tends to 0. Now this is f3x plus f3h plus 2 divided by 3, and then minus it will be f3x plus f0 plus 2 divided by 3 whole divided by h. Now f3x and f3x will cancel and f2 will also cancel. So we'll get this as limit h tends to 0 f3h minus f0 upon 3h, which is nothing but simply f dash 0. And the question, it is given that f dash 0 is 2. So basically f dash x is constant, and if we integrate this, we'll get fx equals 2x plus c. Now we know that when x is 0, y is 2. That means value of c is 2. So this function fx, it is given by 2x plus 2. So for this question, f dash x is equal to f dash 0. That's true. And fx is a linear function. So the correct answers are A and C. Now here the question is, prove that the function is differentiable at alpha if and only if there exists a function g which is continuous at alpha and satisfies fx minus f alpha, and it is equal to gx into x minus alpha. Now this statement, it is bijection, that A implies B and B implies A. So we have to prove it in two parts. In the first part, we'll prove that if gx is continuous at x equals alpha, then f is differentiable at x equals alpha. Now if we write gx is fx minus f alpha upon x minus alpha. Now if we write f g alpha negative, it will be f alpha minus h minus f alpha upon minus h, with this limit h tends to 0, and g alpha positive will be this limit h tends to 0, and will be this f alpha plus h minus f alpha upon h. Now since it is continuous, both of them, they must be same. Now this is nothing but this is f dash alpha negative and this is f dash alpha positive. So if g alpha negative is equal to g alpha positive, we can write f dash alpha negative is equal to f dash alpha positive. That means this function f, it is differentiable at alpha. Now we are going to prove it other way around. Now we know that f is a differentiable function at alpha. So f dash alpha negative will be this limit h tends to 0 f alpha minus h minus f alpha upon h, and basically this is nothing but this is g alpha negative, and the same way f dash alpha positive will be this limit h tends to 0 f alpha plus h minus f alpha upon h, and this is g alpha positive. And also if you look at this gx, then it is fx minus f alpha upon x minus alpha, then g alpha will be equal to this limit x tends to alpha fx minus f alpha upon x minus alpha, and that will be equal to f dash alpha. So that means this is also equal to g alpha, which means this function g, it is continuous. So f is differentiable at alpha if and only if there exists a continuous function gx which satisfies this given condition. Now here the question is, we are given this function f such that f x plus fy, it is equal to f of fx plus fy, and it says f of h is equal to h for h lying between 0 and epsilon, where epsilon is a small quantity. Now we take this limit h tends to 0, then clearly f0 is 0. Now if we put y as h, we can write f of x plus fh, it will be equal to f of fx plus fh. Now fh is simply h, so we can write fx plus h, it is equal to f of fx plus h. Now in this, if we put y as 0, we can write fx plus f0, which is 0, that is equal to f of fx plus f0, which again is 0. So we can write fx as f of fx. So this f of fx is actually fx. So we can write fx plus h minus fx, and we'll divide everything with h. Then this is equal to 1, and we'll take this limit h tends to 0. Now this is nothing but this is f dash x. So we'll get f dash x equals 1. Now we integrate this, we'll get fx equals x plus c. Now f0 is 0. That means value of fx is simply x. And that is the answer to this question. Now here the question is, we are given this function f, which is thrice differentiable, and it says fx plus y equals f x minus y plus y into f dash x plus y plus f dash x minus y. And in this, we are given that f0 is 0, f dash 0 is 1, and f1 is 2. Now what we'll do is, for this question, we'll put y as x. If we put y as x, then we'll get f2x as f0, which is 0, plus x into, now this is f dash 2x plus f dash 0, and f dash 0 is 1. So it will be f2x equals x into f dash 2x plus 1. Now we'll differentiate this. We can write f dash 2x into 2, it will be equal to f dash 2x plus 1 and plus this x as it is, and then will be this f dash 2x into 2. Now this f dash 2x will cancel once. Now again we'll differentiate, so we'll get f double dash 2x into 2, and it will be equal to x into f triple dash 2x into 4 plus 2 into f double dash 2x. Now 2 into f double dash 2x will cancel. So from here we'll get f triple dash 2x equals 0, or simply f triple dash x equals to 0. Now we integrate this, we'll get f double dash x equals a. Now we integrate this, we'll get f dash x equals ax plus b. And if we integrate this, we'll get fx equals ax square by 2 plus bx plus c. Now f0 is 0, then clearly c is 0. Now f dash 0 is 1. Now we put f dash 0. F dash 0 is 1. That means value of b is 1. So b is 1, c is 0, and f1 equals 2. Now f1, it will be a by 2 plus 1, and it is equal to 2. That means value of a is 2. So this fx is actually x square plus x. And that is the answer to this question. Now the question is, we are given this function fx, which is defined as mod of fx minus fy, that is less than equal to 2 times mod of x minus y to the power 3 by 2. Now we can rearrange this as fx minus fy upon x minus y, and it is less than equal to x minus y to the power 1 by 2. And what we'll do is, we'll take this limit y tends to x both sides. Now this is f dash x will be less than or equal to 0. Now modulus cannot be negative. So from here the only condition that we'll get is f dash x equals to 0. That means this fx, it is a constant function. Now if it is constant, its value is same at all points. So if f0 is 1, this fx is simply 1. So we have this constant function fx, which is 1. Now we have to find this integral, which is from 0 to 1, and then f square x, and this is simply 1 dx, and 1 dx is 1, and that's your option C. Now here the question is, if f is a differentiable function, so it's fine. fxy equals fx plus fy plus x plus y minus 1 upon xy for all xy greater than 0, and f dash 1 is to find the value of greater function of f e to the power 100. Now what we'll do is, we'll find the value of f1. We'll put x and y as both 1. So it'll be this f1, and it'll be this 2f1, and here it will be this 1. So from here we can say value of f1, it will be minus 1. Now we'll write f dash x. Now we'll write f dash x as this limit h tends to 0 f x plus h minus fx upon h, and we'll write this as limit h tends to 0, and this is fx into 1 plus h upon x minus fx whole divided by h. Now we'll use this formula, fxy is fx plus fy plus x plus y minus 1 upon xy. So we'll write this as limit h tends to 0. Now this is fx plus f1 plus h upon x, and then plus x plus 1 plus h upon x minus 1 upon x plus h minus fx whole divided by h. Now this fx and fx will cancel, and this 1 and 1 will also cancel. Now what we'll do is, we'll add 1 and subtract 1. So we can write this as limit h tends to 0, and this is f1 plus h by x, and we can write this plus 1 as minus of minus 1, and we know that minus 1 is f1. So this first part will be f1 plus h upon x minus f1 upon h, and then plus this limit h tends to 0, and if we simplify this, we'll get this as h upon x minus h whole divided by h, and here this is x plus h. Now here if we multiply and divide it with x, now this is derivative of this function at 1, so it will be this f dash 1 by x, and this is your f dash x plus, now here we can cancel h with h, so it will be 1 upon x minus 1, and here we have this 1 upon x, so it will be this 1 upon x into x minus 1. Now we are given that f dash 1 is 2, so if we put f dash 1 as 2, so it will be 2 upon x plus 1 upon x square minus 1 upon x, or we can write f dash x is 1 upon x plus 1 upon x square. Now we integrate this function, we can write fx equals log x minus 1 upon x plus c. Now f1 is minus 1. So if we put x as minus 1, this is minus 1, 0. Minus 1 plus c, that means value of c is 0. So in this case, our function fx is log x minus 1 by x. Now we need to find the value of greatest integer function of f e to the power 100. Now first we'll find f e to the power 100. Now this f e to the power 100, it will be this 100 minus e to the power minus 100, which is 100 minus some small value. And if we take greatest integer function of f e to the power 100, it will be 100 minus h, which is 99. So answer to this question is 99. Now the question is, let fx be a positive differentiable function satisfying f x plus y by 2, that is equal to under root of fx into fy for all xy belongs to R and f dash 0, it is equal to 2. Find fx. Now we'll write f dash x. Now f dash x is this limit h tends to 0 f x plus h minus fx upon h, and we'll write this as limit h tends to 0, and this is 2x plus 2h by 2 and minus f 2x plus 0 by 2 upon h. Now will be this limit h tends to 0, and here it will be under root of f2x into f2h minus, and it will be under root of f2x into f0 whole divided by h. Now what we can do is we can take under root f2x common. Now here also, if we put, now we take it common, then we can write this limit h tends to 0, and then it will be this under root f2x, and here it will be under root of f2h minus under root of f0 whole divided by h. Now this is under root of f2x, and we can write this as limit h tends to 0 f2h minus f0 upon h, and it will be under root of f2h plus under root of f0. Now we'll multiply and divide it with 2. Now we have replaced fx with under root f2x into root f0. So we can write root f2x as fx upon under root f0. So it will be 2 times fx upon under root f0, and here it will be this f dash 0, and here it will be 2 times under root of f0. Now this 2 and 2 will cancel. We'll get this as f dash 0 into fx upon f0. And the question it says f dash 0 is 2. So we'll put f dash 0 as 2. And this question, they are also supposed to provide the value of f0. So I think they have taken value of f0 as 1. So we'll take value of f0 as 1, and we'll say it is given in the question, because there is no way we can find the value of f0 with the given condition. So now this f dash x, it will be 2 times fx. Now we can write f dash x upon fx, it is equal to 2. Now we integrate, we can write log fx equals 2x plus c, or fx equals e to the power c into e to the power 2x. Now when x is 0, f is 1. That means e to the power c is 1. So our function fx in this case, it will be e to the power 2x. So I think one condition that is needed with this question is value of f0 is 1. Now here the question is, if f is defined from R to R and it is differentiable at C belongs to R and fc is 0, it says if gx it is equal to mod of fx, then we have to discuss differentiability of gx. Now if we look at g dash c negative, it will be this limit h tends to 0 positive mod of f c minus h minus mod of fc upon minus h. Now we are given that fc is 0. So we can write this as this limit h tends to 0 positive mod of f c minus h upon minus h, or we can write this as this limit h tends to 0 minus, and we'll take this h inside, so it will be this f c minus h and then minus fc, because fc is 0, we can just add or subtract fc upon h. Now this is left hand derivative at c, so this is equal to minus mod of f dash c. And the same way, if we write g dash c positive, it will be this limit h tends to 0 positive mod of f c plus h minus mod of fc upon plus h. Now this is 0, we can write this as limit h tends to 0 mod of f c plus h minus fc upon h, which is mod of f dash c. Now this function is differentiable, then both these values, they must be equal. So minus mod of f dash c must be equal to mod of f dash c, and it is only possible if f dash c is 0. So this gx will be differentiable if f dash c is 0, and that's your option D. Now here the question is, if f is a differentiable function, sets fine f dash x equals f dash minus x for all x belongs to R, then which of the following is correct? Now if we integrate this, we can write fx and it will be equal to minus f minus x plus c, or we can write fx plus f minus x will be constant. That is, if f1 equals f2, then we need to identify whether f minus 1 equals f minus 2. Now if we put x as 1, we can write f1 plus f minus 1, it is c, and it will also be equal to f2 plus f minus 2. Now if f1 equals f2, then clearly from here we can say f minus 1 must also be equal to f minus 2. That means this statement A is correct. Now in this, if we put x as 0, we can write c as 2 times f0. So from here we can say fx plus f minus x, it should be equal to 2 times f0. That means this option D is also correct. Now if you look at this option B, then we are given 1 by 2 fx plus 1 by 2 fy, it is equal to f 1 by 2 x plus y. Now if you look at this option C, it says let fx be an even function. If it is even, then f minus x is equal to fx. So in that case, it will be 2 times fx and it will be equal to 2 times f0. So from here we'll get this condition that fx equals f0, and this f0, it may be 0 and it may not be 0. So this C is not necessarily true. Now in B, if we replace y with minus x, we can write fx plus f minus x will be 2 times f0. which matches with our condition. But then in one special case, this condition is equal to this condition. But generally for different values of x and y, this condition is not true for our function. So this option B may not be correct. So the correct options are only A and D. Now question number 4 is, the function f is defined on R to R and let it be a twice differentiable function such that f dash x minus f dash y will be less than or equal to 3 times mod of x minus y. Now if we interchange x and y, we can write this as f dash y minus f dash x will be less than or equal to 3 times mod of x minus y. That is, from here we can clearly say that this mod of f dash x minus f dash y, it is less than or equal to 3 times mod of x minus y. Now what we'll do is, without loss of generality, we'll assume that x is greater than or equal to y, and when we fix x and y, we'll define this t as some x minus y, and this t will be greater than or equal to 0. Now if we choose some h which lies between 0 and t, if we take this x as y plus h, we can write this as mod of f dash y plus h minus f dash y will be less than or equal to 3 times mod h. Now what we'll do is, we'll integrate both sides from 0 to t. Now we know that integral of 0 to t mod fx dx, it is greater than or equal to mod of this integral fx dx. So we'll write this mod of integral from 0 to t f dash y plus h minus f dash y dh, it is less than or equal to from 0 to t 3 mod h dh. Now if we integrate this function, we'll get this as f y plus h from 0 to t minus f dash y into h from 0 to t, it is less than or equal to 3, and this is h square by 2 from 0 to t, and it'll be mod f y plus t minus fy minus f dash y into t will be less than or equal to 1.5 t square. Now t is x minus y. If we put x minus y, it will be mod of fx minus fy minus f dash y into x minus y will be less than or equal to 1.5 x minus y square, and this is what we need to prove. Mod of fx minus fy into f dash y x minus y, it is less than or equal to 1.5 x minus y square. Now B part is, find the largest and smallest possible value of f double dash x under the given condition. So for that, we'll use this condition, which is mod of f dash x minus f dash y, it is less than or equal to 3 mod of x minus y. Now we can also write this as mod of f dash x minus f dash y upon x minus y, it is less than or equal to 3. Now we'll take this limit y tends to x. Now we take limit y tends to x, then on the left hand side, this expression is nothing but f double dash x. So we can write this as mod of f double dash x will be less than or equal to 3. Now when mod x is less than a, x lies between minus a and plus a. So we can write f double dash x, it will lie between minus 3 and plus 3. So its smallest value is minus 3 and its largest value is plus 3. Now question number 4 is, let f be a twice differentiable function in the open interval -1 to 1 such that f0 is 1. Suppose f also satisfies fx greater than or equal to 0, f dash x less than or equal to 0, and f double dash x is less than or equal to fx for all x greater than 0, then show that f dash 0 is greater than or equal to minus root 2. Now it is given that this function f, it is a twice differentiable function, so we can use Taylor's polynomial theorem. We can write fh will be equal to f0 plus f dash 0h plus f double dash theta h square upon 2, where theta lies between 0 to h. Now since f double dash x, it is less than or equal to fx, we can write f double dash theta will be less than or equal to f theta. Now since f dash x, it is less than or equal to 0, it simply means fx is a decreasing function, and if fx is decreasing, then f0 will be greater than f theta. So f theta will be less than or equal to f0. fh, it will be less than or equal to f0 plus f dash 0h plus f0 h square by 2. Now f0 is 1. So we can write fh, it is less than or equal to 1 plus f dash 0h plus h square upon 2. Now we know that f double dash x is less than or equal to fx. So we can say this fh will be greater than or equal to f double dash h. Now we'll integrate both sides from 0 to x. So we can write f dash x minus f dash 0 will be less than or equal to x plus f dash 0 x square upon 2 plus x cube upon 6. Now we'll integrate this once again from 0 to x. Here will be fx minus f0 minus f dash 0x, and it will be less than or equal to x square by 2 plus f dash 0 x cube by 6 plus x to the power 4 by 24. Now we'll take f dash 0 together. So we can write f dash 0 x plus x cube upon 6, it is greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 plus fx minus f0. Now f0 is 1 and fx is always greater than or equal to 0. So from here we can say f dash 0 into x plus x cube upon 6 will be greater than or equal to minus x square upon 2 minus x to the power 4 upon 24 minus 1. And from this we can write f dash 0 will be greater than or equal to minus x square by 2 minus x to the power 4 upon 24 minus 1 upon x plus x cube by 6. I'll be true for any x which lies in the interval 0 to 1. Now this function on the right, it is an increasing function. So this f dash 0 will always be greater than or equal to the value when the value of x is 1. So if you put x as 1, we'll get this as minus 1 by 2 minus 1 by 24 minus 1 upon 1 plus 1 by 6. So it will be minus 37 upon 28, which is nearly minus 1.32.
So from here we can say this f dash 0 will be greater than or equal to minus root 2, and that is the answer to this question. Now question number 2 is, we are given a function f which is defined on integers such that f0 is unequal to 0 and f1 is equal to 0. Assume that f satisfies the following two equations. We need to find set of values of this function f. That is, we need to find a range of this function. Now from this first equation, if we put x as 0 and y equals 0, we'll get f0 equals f0 plus f0 minus f0 square. I'll cancel. So from here we can say either f0 is 0 or value of f0 is 1. Now we are given that f0 is unequal to 0. That means it is not possible. So the value of f0 will be simply 1. Now what we'll do is, in this second equation, we'll put y as 0. Now if we put y as 0, we'll get this as fx into f0 will be f0 into fx into f0. Now f0 is 1. So from here we can write fx square minus fx equals 0. That means value of fx is either 0 or value of fx is 1. So this function fx can take only two values, 0 and 1. That means range of this function is simply 0 and 1, and that's your part A. Now in part B it says that assuming that there is a non-zero integer a such that f is unequal to 0, then prove that the set B fb unequal to 0 is infinite. So now we have any non-zero integer a such that f is unequal to 0, and since range of this function is 0 and 1, it means fa it is equal to 1. Now we need to prove that if f is equal to 1, then there exist infinite points b such that fb is unequal to 0, that is fb is equal to 1. We'll prove that f minus na will be 1 for all n belongs to natural numbers, and we'll prove this result using induction. So let the statement be Pn. Now first we'll prove P1 is true. Now if we put n as 1, we'll get f minus a equals 1. Now in this equation, if we put x as 0 and y as a, we'll write this as f minus a into f0 into fa will be equal to f0 into f0 into fa. Now f0 is 1 and fa is also 1. So from here we can say f minus a equals 1, that is P1 is true. Now the second step is we let Pk be true. So if Pk is true, that means f minus k is equal to 1. From here we have to prove that Pk plus 1 is true. Now Pk plus 1 is f minus k plus 1a. For that, what we'll do is, in this second equation, we'll put x as minus ka and we'll put y as a. We can write f minus k plus 1a into f minus ka into fa will be equal to f0 into f minus ka into fa. Now f minus k is 1, fa is 1. So from here we can say f minus k plus 1a is also 1. So P1 is true, and assuming Pk to be true, Pk plus 1 is true. That means from induction we can say that the statement Pn is true. So if we have any non-zero a, then we'll have infinitely many points where this function is non-zero. Now question number 16 is,
consider real valued function f satisfying fx plus 1 equals fx for all x belongs to R. That means this function is periodic with period 1. We are given that gt is this integral from 0 to t fx dx, and we have defined this function ht as this limit n tends to infinite g t plus n upon n. Now if we look at gt plus n will be nothing but 0 to t plus n fx dx. Now we can write this as this integral from 0 to n fx dx plus n to n plus t fx dx. Now this function is periodic with period 1. So we can write this as n into this integral from 0 to 1 fx dx, and then plus, now this is from nt to nt plus a, and it will be from 0 to t fx dx. So we can write this function h as this limit n tends to infinite n, this integral from 0 to 1 fx dx plus this integral from 0 to t fx dx upon n. Now we split it in two parts. This n and n will cancel, and 1 upon infinite will be 0. So this ht will be nothing but will be this value from 0 to 1 fx dx, which is a constant function. So this ht, it is defined for all t belongs to R, and it is independent of t, and that's here option C. Now here the question is, find a function continuous and differentiable for all x and satisfying this functional relation f x plus y into f x minus y, and it is equal to f square x, and it is given that f0 is unequal to 0. Now in this, what we'll do is we'll put y as h, then we'll get this relation that fx plus h into fx minus h, it will be equal to f square x, and if we put x as 0 and y as x, then we can write f of x into f of minus x, it will be equal to f square 0. Now what we'll do is we'll write f dash x. Now this f dash x will be this limit h tends to 0 f x plus h minus fx upon h. Now what we'll do is we'll write this fx as f square 0 upon f minus x. So it will be this limit h tends to 0 fx plus h minus f square 0 upon f minus x divided by h. Now we can write this as limit h tends to 0 f x plus h into f minus x minus f square 0 upon f minus x into h. Now somehow we have to express it as x plus y and x minus y. So what we'll do is we'll write this as this limit h tends to 0, and this is f h by 2 plus x plus h by 2, and here it will be this f h by 2 minus x plus h by 2 minus f square 0 whole divided by f minus x into h. Now this is fx plus y into fx minus y, and we know that it is equal to f square x. So it will be this limit h tends to 0, f square h by 2 minus f square 0 upon f minus x into h. Now we'll use a plus b into a minus b, so we can write limit h tends to 0, and this is f h by 2 minus f 0 upon h, and we'll write this as f h by 2 plus f 0 upon f minus x. Now this is nothing but this is f dash 0 if we multiply and divide it with 2. So it is 1 by 2 f dash 0, and here it is 2 f0 upon f minus x. Now this 2 and 2 will cancel. So now we have f dash x as f dash 0 into f0 upon f minus x. Now we have already proved that fx into f minus x is f square 0. So we'll replace f minus x with f square 0 upon fx. So it will be this f dash x equals f dash 0 into fx upon f0. Now we can write this as f dash x upon fx, and this is equal to f dash 0 upon f0, and this is some constant, say a. Now if we integrate this, then we can write log fx equals ax plus c, or fx is e to the power ax into e to the power c, and e to the power c is some other constant, say capital F. So it is a into e to the power ax, and that is the answer to this question. Now this third question is, we are given that fx plus 1 equals 1 by 2 fx. Now let an equals from 0 to n fx dx. We need to find this limit n tends to infinite an. Now in this equation, if we put x as x plus n minus 1, then we can write fx plus n as 1 by 2 f x plus n minus 1 will be equal to 1 upon 2 square f x plus n minus 2, and using iteration will eventually come to 1 upon 2 to the power n into fx. Now we need to find this integral an, which is from 0 to n fx dx. Now we need to find this limit n tends to infinite an, which is this summation r varies from 0 to infinite integral from r to r plus 1 fx dx. Now what we'll do is, we'll replace x with t plus r. Then we can write this as this summation r varies from 0 to infinite. Here will be from 0 to 1 ft plus r dt. Now using this relation, we can write f t plus r as 1 upon 2 to the power r into ft. So it will be this summation r varies from 0 to infinite 1 upon 2 to the power r, then this integral from 0 to 1 ft dt. Now this is nothing but an infinite GP. Now sum of this GP will be a upon 1 minus r into this integral from 0 to 1. Now ft dt is same as fx dx. So we can write this as 2 times this integral from 0 to 1 fx dx, and that's your option D. Now question number 3 is, let this function f be defined from r to r such that mod of f x plus y minus f x minus y is always
less than or equal to y square. Now we need to show that fx is x by 2 plus c, where c is a constant. Now what we'll do is we'll try and rearrange this functional equation. So we'll let this x plus y as some t plus h and x minus y as t. Now we subtract the second from first, we'll get y as h by 2. So we can write this as mod of f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now mod x is less than a, then x lies between minus a and plus a. So we can write minus h square by 4. It is less than or equal to f t plus h minus ft minus h by 2, and will be less than or equal to h square by 4. Now we'll add h by 2. So we can add h by 2 minus h square by 4 will be less than f t plus h minus ft, and will be h by 2 minus h square by 4. Now we'll divide everything with h, and we'll take this limit h tends to 0. Now this value, it is 1 by 2. Now this is nothing but this is f dash t, and this limit, it is also 1 by 2. So from here we can say this f dash t, it is 1 by 2. Now we integrate this function, we write ft as 1 by 2 plus c, or we can write this function fx will be simply x by 2 plus c, where c is a constant. And this is how we solve such questions. Now here the question is, for every twice differentiable function f from r to minus 2 to 2, and we are given this condition that f0 square plus f dash 0 square, and it is equal to 85, which of the following statements is or are true. Now we know that codomain for this function is from minus 2 to 2. That means any value of fx will lie between minus 2 and plus 2. Now here in this case, f dash 0 is not equal to 0. And if f dash 0 is not equal to 0, then it will be either increasing or decreasing in the neighborhood of 0. So we'll always have this small interval from minus delta to plus delta, where this function will be a 1-1 function. So that means this statement 1 is always correct. Now the next one is, there exists x0 in the interval minus 4 to 0 such that mod of fx0 will always be less than or equal to 1. Now what we'll do is, we'll apply Lagrange's mean value theorem in this interval. There will be some x0 in minus 4 to 0 such that f dash x0 will be equal to f0 minus f minus 4 upon 4, and we take this mod sign. Now we know that minimum value of fx is minus 2 and maximum value is plus 2. So the maximum value of f0 minus f minus 4 will be 4. So it will always be less than or equal to 1. That means this statement B is also correct. Now this third one, it is limit x tends to infinite fx, it is equal to 1. This may not always be true. So we have this bounded function. If we can choose this bounded function fx as sum 2 sine ax, then it will satisfy all these conditions. And if we take this x tends to infinite, it will be this oscillating value from minus 2 to plus 2. And here we can also change this amplitude. We can take any value between 0 to 2. So this option C, it is not always correct. Now this D is, there exists alpha in minus 4 to 4 such that f alpha plus f double dash alpha is 0 and f dash alpha is unequal to 0. Now this option, it is the trickiest one. Now for this fourth one, what we'll do is, we'll assume function gx
and we let this gx as fx square plus f dash x square. Now if we find g dash x, then g dash x will be 2fx into f dash x, and here it will be 2f dash x into f double dash x. Now we'll take 2f dash x common, and then we'll have fx plus f double dash x. Now if we look at g0, g0 will be f0 square plus f dash 0 square, and which is given as 85. Now what we'll do is, we'll consider two separate intervals. First interval when x lies between -4 and 0, and second interval where x lies between 0 and 4. Then from this statement we can say there exists some point x0 which lies between -4 and 0 such that mod of f dash x0 will be less than or equal to 1. In the same way we can prove it from 0 to 4 also. So here we'll get some x1 lying between 0 and 4 such that f dash x1 it is less than or equal to 1. Now if f dash x0 is less than or equal to 1, we can write f dash x0 square will also be less than or equal to 1. Then in that case this gx it will always be less than or equal to, now maximum value of fx is 2, so it will be this 4 plus 1, and there will be 5. So gx0 it is less than or equal to 5, and gx1 is also less than or equal to 5. Now if we look at this interval between x0 and x1 which lies between -4 and +4, this function will take some value which is less than 5, and it'll end at value which again is less than 5, and at 0 this value is 85. So this function it will increase and decrease in some way, and then this value is going to come back to this lowest value. Now since this function is continuous and differentiable, there exists at least one point alpha in the interval x0 and x1 where g dash alpha it is equal to 0. Since this alpha belongs to x0, x1, it will also belong to -4 and 4, and then g dash alpha equals 0 means twice f dash alpha into f alpha plus f double dash alpha will be equal to 0. Now f dash alpha it cannot be 0. Now in this case this value at alpha will be maximum, so this g alpha will be f alpha square plus f dash alpha square, and it should be greater than or equal to 85. Now if f dash alpha is 0, f alpha should be under root 85, but it cannot take the value greater than 2. So that means this f dash alpha it can never be 0. So the only condition that we'll get here is f alpha plus f double dash alpha it must be equal to 0. That means this option D is also correct. So the correct options are A, B and D.